All right, third example. The first year student dropout rate at a particular college, some college, has historically been around 20%. Okay. Of course, we would like everyone who comes to college to be able to stick it out and succeed and graduate. So we're going to try a new retention program to help those students stick around and succeed. So in its trial year, 206 out of 1852 students, first year students, drop out. So let's test at 1%. Okay, so this is a typical question setup. You know, if you pull out an exercise or I give you a question on an exam, this is the kind of thing that you'll be given as a setup. And I might give a little more details. I might say like, you are formulate a hypothesis test, and find the p-value, test at 1%. Okay, so this is like the setup that you would be given. Now, when I say formulate a hypothesis test, if you're not explicitly told, part of that is to say what the null and alternative hypothesis are. So your job here is to say, what is the null hypothesis? What is the alternative hypothesis? And then run the test to find the p-value. And the results of the experiment are given in the question because you need those to run your test, but they are not going to factor in the hypotheses because the hypotheses are supposed to come before the experiment. Your hypotheses have to be based on the other stuff here, which is basically just the first two sentences in this setup. So our null hypothesis is going to be the old number we're comparing to. So before the dropout rate was 20%, we're trying to see if we could change that. So if the new retention program does nothing, then it's still going to be 20%. If the new retention program works, it's going to be something else. So our null hypothesis is that the dropout rate is still 20%. I'm going to write that in decimal form, 0.2. Alternative hypothesis. Now, I've said that the default is not equals, and we could use that here. We could say the alternative hypothesis is not equals 0.2. But if with the retention program, if the dropout rate is worse, we're not going to use it anymore. The retention program is going to cost effort and money, and it's only going to be worthwhile if the dropout rate is better. And what's better? Well, lower. We want fewer students to drop out. So I think that because what we want to know is the retention program working, the alternative hypothesis we're looking for is really less than. We would like the dropout rate to be lower than it was before we instituted this new program. And the way that our book writes things, that means that this is going to be, greater or equals. So the null hypothesis is really this 0.2 number, but our book likes to set things up so that whatever is not in the alternative hypothesis is part of the null hypothesis. So we are going to use a less than for alternative hypothesis this time because in some sense we don't care if it's higher. Now, why didn't I do that on my fungus plant example earlier? Like, we're not going to use the treatment if it makes things worse. Well, we could have. There I said, well, let's stick with not equals because it's still valuable to know if the treatment makes things worse. And that would be true here too. So we could have used we want the survival rate to go up. In that earlier example, we could have used greater than, and it would totally have made sense. And here we could use not equals, and it would totally make sense. We want to know if the retention program is hurting or helping. If it's helping, great, we'll keep it. If it's hurting, that'll be useful information when we try to do a better retention program. You know, we have to try to like learn from our mistakes, right? We want to know if it's hurting. Okay, so not equals would be fine, less than will be fine. I'm going to go with less than here because we used not equals before, and I want examples where we do things different ways. So let's flip over to Minitab and put all these numbers in. Stat, basic statistics, one proportion. So 206 out of 1852 dropped out. And we are comparing to the old number of 20%, 0.2. And this time I'm going to change my alternative hypothesis. I want the dropout rate to be lower than 0.2 because my retention program is supposed to help. Hit OK, see what we get. So the dropout rate with our retention program was 11%, quite a bit lower than 20%. And indeed, the p-value to 3 decimal places is 0. Let me get lots of decimal places here. So the most decimal places I can get is 16, and it's actually 0 to 16 decimal places. That doesn't mean it's going to be 0, period. It's probably, the numbers are going to come in somewhere. It's just that we're way down the tail of the bell before you get to 0.2. Okay, so the p-value isn't really 0, it's just 0 to lots and lots and lots of decimal places. Certainly, this is less than our testing level. So let me flip back to Word. Our p-value is 0 to 16 decimal places. That is definitely less than 1%, which was our testing level. So we have strong evidence that the retention program lowered the dropout rate. Okay, so the dropout rate is now lower than 20%. I'm going to add something to this question that was not part of the original question. Let's do a 99% confidence interval. Okay, because the p-value is so small, it seems like maybe this new program didn't just lower it a little, maybe it lowered it a lot because the results of our experiment were so far away from the old number of 20% that the p-value was super tiny, 0 to 16 decimal places. That's extraordinarily small. So let's run the 99% confidence interval. I'm going to flip back to Minitab. And under options, let's do a 99% confidence interval. And because this is a less than, it's doing this weird one-sided confidence interval, I'm going to change it to not equals so that it does a confidence interval with bounds on both sides, which is what we're used to. Okay, so this is now running a different hypothesis test than it did before. It's running the not equals one, but with that not equals there, it'll give me the confidence interval with bounds on both sides. Okay, so my 99% confidence interval goes from about 9% to 13, so 0.93 to 131. Okay, so my 99% confidence interval is 0.093 up to 0.131. Okay, so now we're saying not only do we have strong evidence that the retention program helped, the 99% confidence interval actually gives you an idea of what the dropout rate is now. So under the new retention program, we're 99% sure, we're quite sure that now the dropout rate is between like 9 and 13%, which is way under 20%. So not only have we lowered the dropout rate, we have a good idea of how much we've lowered it. So in this case, I would say that the confidence interval is more useful. So in this case, the confidence interval is a more useful result than the hypothesis test, arguably, I guess. And usually I tend to like confidence intervals better because it doesn't just tell you, like it tells you where the number is going to be. So if you want the number to go down, hypothesis test only told us that it went down. It doesn't tell us how much it went down. There are times when hypothesis test is maybe better, like in our example from the previous class when we're trying to estimate who won the election. They're like knowing the exact percentage of the vote that a particular candidate got is in some sense less important than knowing the chances that they got more than half. The hypothesis test is going to tell you what is the probability that they got more than half, kind of. And their hypothesis test is probably better, but most of the time you want an idea of what the real p-value is, and you want to know what your error is, how close that estimate is going to be, and that's a confidence interval, what you're talking about. So hypothesis tests get run a lot, but I think that, in my opinion, confidence intervals are more useful. So that's it for our third example. I have one more.